We are going to talk about mechanical properties of matter, and yes, we are going to talk about elastic bodies. So, elasticity has a very important role to play, not just in our daily life, but there are so many phenomena and so many applications of elastic properties of matter. All of this with me, Shreyas, your physics master teacher at Vedantu, going live. Hi Ishpreet, hello Ramya, and let me quickly brief you what we are going to do in today's Nurture Lecture 1 of mechanical properties of matter. Now we're going to start with what is deformation, what is the different types of behavior of matter. Then we'll also go to different types of stress and strain. Yep, you take stress during the exam and there is stress in physics too. So we're going to talk what is stress, what is strain, what are the different formulas. The most important law, that is Hooke's principle, the Hooke's law for elastic bodies. And yes, then we're going to talk about the different types of modulus of elasticity for the three kinds of deformation. And then we'll go to the energy stored, and finally we'll end the class with stress strain graphs and their applications. So those of you who do not know me, I am Shreyas. Some of the students also call me Captain Shreyas. Yep, because probably I'm the captain for your journey towards success when you're going to crack JEE 2023. So welcome aboard. Having taught almost like for more than 10 years, I know what it takes to get into IIT. I know what kinds of struggles you need to do in this course of 2 years. So stay with me in Nurture series, because this is a long-term batch for all of you on YouTube, which is going to cover the entire 11th standard syllabus. So it doesn't matter even if you are a 12th standard student or even if you are a 9th standard student who wants to study 11th standard portions. You are all welcome aboard. So for that, you need to first of all hit the subscribe button in case you haven't done so even till now, because then you will miss the classes if you have not yet subscribed. And also a lot of thanks for smashing that like button down there. Hello Aishwarya, hi Ramya, hello Harita, welcome aboard. A warm welcome with all your lovely hearts. Nice to see all of you out here in the next session. This is on-demand class. Reason is, just last week I conducted a poll on our YouTube community, what is the next class you want? And all of you are like, sir, we want mechanical properties, and then you want thermo and fluids and all of that. So I have listened to you. So we will do mechanical properties today. It's a small, sweet, simple chapter. And if you have studied this in school, and if you still have doubts, trust me, this session right now which you are going to attend will help you. It will give you some more knowledge. It will give you a lot of problems practice. And if you have no idea, still this will obviously help you, because this is eventually going to come. And we're going to have so many more sessions in the days to come. So let's begin this class. And yep, let me also tell you all the PDFs will be uploaded very soon on our Enthuse Telegram channel, and the link is there in the description box below. So what is elastic behavior? Okay, you might have heard about rubber band showing elastic property. Yep. Thank you, Rahul Krishna. It means a lot. Very good. I'm so glad that you are back to the next class too. So elastic means it comes back to its original shape or size. Like look at this rubber band. You stretch it, leave it, comes back. Right? It does come back. The tail of a dog. Have you heard about that saying? The tail of a dog never straightens if it's curved. No matter what you do. You hit it, you console it, you advise it, you iron it. Have you tried ironing the tail of a dog? Don't do that. It's cruel. Okay? So, no matter what you do, the tail of a dog, even if you try to turn it, if you twist it, if you try to straighten it, again comes back to its original shape. That's how it is. Yep, it is. But plastic behavior is completely opposite. Like clay. Look at this beautiful example of clay. You might have played with clay in your childhood or even maybe now. Or cheese on your pizza, you bend it, leave it, it stays there. Chewing gum, you bend it, leave it, it stays there. It's not going to come back. Right? So these are plastic bodies. Elastic is a property where the body regains its shape when deformed, and plastic is the property where a body does not regain its shape when it is deformed. It does not come back to its original shape and size. That's what it is. Very good, Ramya. Hi Chandra, welcome aboard. Now, there are different ways in which you can analyze why do bodies actually come back to its original shape, or why do they not come back to its original shape and size. If you think of any object, be it this book, be it this remote, be it my hand, be it this watch, be it your table, be it a steel ball, be it a rubber ball, it's all made of molecules, and molecules are joined together with bonds. So a simple way to analyze it is, imagine the molecules like these masses and the bonds like the spring. If two bonds try to come close to each other, it's like in a movie, the hero tries to go very close to the heroine. The heroine is like, go away. Duriya bhi zaruri hai, basically maintain distance, social distance. Now if the hero goes really far away, the heroine is like, hey, come back, I'm missing you. So that's what happens between any two masses. If they go far away, they are pulled back. Elastic forces, the spring-like forces push them back. If they come very close, then they are again pushed back to their equilibrium position. Now every body behaves in this manner. So when you apply any external force, like let's say you hold an object, or you push an object, or you pull an object, or you just press something, then these bonds get compressed or elongated depending on how you are pulling or pushing it. So exactly what happens is, these molecules, they come close or they go far away, and these spring-like forces come into action. So when you remove this force, if you remove this force, the spring-like forces will push them back over here into their original shape and size. So this external force is your deforming force. I will write it down over here. This external force. So this is basically your, oops, where did it go? Here. So this external force, this external is basically your deforming force, and your internal forces together will try to restore it. So that's why it is called as restoring force. When you remove the deforming force, the restoring force pulls it back. In elastic bodies, is restoring force present or not present? Put it up in the chat box. Hi RR Sanjay, hi Santosh S. Yes, Grey, look, I just conducted a video for strategy for the physics examination. Just watch it, okay? Just conducted a few minutes back. So in an elastic body, what do you suggest? Is there restoring force or is there no restoring force? Come on, think about it. Obviously, there is restoring force. But in plastic bodies, like clay, cheese, or anything which deforms and does not come back, is there any restoring force present? Think about it. It does not come back. So there is no restoring force. So in those kind of bonds, if you compress a spring, that's it. It stays compressed. That's it. Gone. Permanently deformed. It's like, okay, give up. So in plastic bodies, there is no restoring force present. The springs get broken, or the springs are ineffective in pushing it back. That's what happens. Hence, I will classify the objects in the following categories based on the elastic properties. First is elastic body. The second one is plastic body. A plastic body does not regain its shape. An elastic body has two more categories: perfectly elastic and partially elastic. Perfectly elastic means you pull it, it comes back to the exact shape and size. There is no minute difference also, even at nanometer level. You pull it, stretch it or compress it, it comes back exactly the same way it was. But actually speaking, there is no such body. Most of the bodies show that kind of behavior. Okay, you cannot distinguish. So we call it perfectly elastic. But many objects, okay, show partially elastic behavior, as in when you bend it, stretch it or deform it, it comes back, but not so much. So it is not perfectly plastic, it's not perfectly elastic. So somewhere in between. Is that understood, my warriors? Yep. I hope this is clear. Okay. So Ramya, same slide I used yesterday in mechanical properties lecture 4. I'm not sure. Okay. So yesterday I did not conduct any class on mechanical properties. This is the first class. Okay. Cool. Now here is the first question. Which of the following substance has highest elasticity? Is it rubber? Is it steel? Is it clay? Or is it wood? Come on. Very good, Chandra. Very good, Arlene Mishra. Very good, Alna. What do you think? Which of the following substance has the highest elastic property? Is it rubber? Is it steel? Is it clay? Or is it wood? Very interesting question. Some of you saying steel. Some of you saying rubber. Some of you saying again steel. Okay, students are confused between steel, and some of you are confused between rubber. Yep. So, Thayu, it's all uploaded in the Telegram channel, bacha. Yep, if you join. Well, the correct answer is actually steel. It's not rubber. Obviously, clay is not even elastic. Wood, no, it breaks off. I mean, like if you bend it, it breaks. That's it, gone. Okay, it's brittle. Rubber and steel, you are confused. See, rubber is elastic, but not as elastic as steel. If you bend steel, like the one I can show you probably over here, then, you know, it tries to regain its shape and size. See, look at this steel scale. I bend it. See, so much of bending. It comes back. You can see it came back to its original shape and size. But rubber, when you bend it, it comes back, but it might show some plastic behavior. It might bend permanently as well. So rubber is not as elastic as, you know, steel. That's what the problem is with the rubber. It can show. If you stretch a rubber band too much, you would have seen that the rubber band becomes elongated. Yep. Or your pants. If you have an elastic band, you stretch it too much. Or you become too fat. You would have noticed you become too fat, for example, or some friend of yours would have become too fat. Suddenly after 1 month, you will realize if you become thin, then the pant no longer fits you because the rubber has already stretched. Have you noticed this? Have you noticed this? If you have become fat and suddenly become thin, you would have noticed your pants no longer fit you. It becomes really big. Okay, anyways, now let's talk about stresses. What is stress? Stress is essentially intensity of the force. Let me tell you what stress is. Stress is the intensity of the force. I'll give you a very simple example and you'll understand it. Arun says yes, looks like Arun was really fat some days back and then he has seen that his pants no longer fit him. Very good, Arun. So here we have a cross section. Imagine these arrow marks together show you the force's direction. Together this is 10 Newton force. Okay, together this is 10 Newton force. Now I take a small cross section and there are, you know, it's not as big as this, it's smaller, and there are same arrow marks but more in number, but in spite of that they together add up to 10 Newton. They add up to 10 Newton because now they are on the smaller area, so they have to be closely packed. So that's why more number of arrow marks, but you know, close to each other. Still the total force is 10 Newton. You will see that here the force is distributed on a large area. Here the force is distributed on a small area. So when the force is distributed on a small area, it is more intense. It is intense. The density is more. Okay, the intensity is more. Here the intensity is less. So here I would say the stress is going to be less. Here the stress is going to be more. So the compactness of the force. If the force is on a big area, less stress. If the force is on a very teeny mini area, more stress. I'll give you a simple example. Okay, just try this. If you have a pen, everybody come on, let's do this. I have a pen and this is a hand and I'm just going to apply some force from the top. See this hand from the top, it's going to apply the force. Just do this on your palm. Are you feeling the pain? If you are feeling the pain, raise your hands up. Okay, Thalu, I know, I am aware of that problem. There are some issues, like I said, it needs to get uploaded. It's going to take some time. Maybe some of the sessions would not have been uploaded. It will take some time. Give me a week. By this week, I'll make sure it is sorted. Okay? Yeah. So, okay, Ramya, no problem. So, do you feel that pain? Yes. Now, reverse that pen and hold it like this. Now, apply the same force. Now, you don't feel the pain. You reverse the pen. Yeah? Why is that? Same force, but the area on which the force is applied is different. When you do this, the pointed point is touching your hand or your palm, then you feel the pain because the stress is more. So that's what stress is. Did you now feel stress? How many of you felt the stress? Yeah? So that is what stress is. Stress is the force acting per unit area. Applied force by the area. Area is less, stress is more. Force is more, stress is more. That's what it is. Perfecto. And yes, you realize the moment you reverse the pen, there is no stress, there is very less stress. You don't feel that pain. Perfecto. Excellent. Now there are three kinds of stresses. Yep, because there are three kinds of deformation that happens every day around us. Any kind of deformation can be classified into one of these three categories at a minute level. Anything, any deformation. You hit somebody, his face gets deformed, okay? Or basically you press somebody, his body gets deformed. All these deformations come under one of these three categories. The first category of deformation is called longitudinal. Longitudinal means you stretch or pull along the length or push it along the length. Like for example, the column in your house, it gets pushed, it gets compressed because of the weight of the building. Or if something is hanging, let's say you hang, your hands are under that stress along that length. That is called as longitudinal stress. Longitudinal stress. Look at this. Are these two diagrams making it clear what is longitudinal stress? But there is a small difference between the two. The top one is tension. The bottom one is compression. Raghav, I'll definitely let you know, bacha. Stay till the end. I'll show you how to enter into 2023 VIP subscription. Okay, don't worry. All right. So this is tensile stress. This is compressive stress. I hope it gives you an idea what stress is. Now Now Rahul, very valid point. Isn't stress and pressure the same thing? No. It feels the same, but it is not technically the same thing. I'll tell you, I'll give an example. Imagine this is a Pandu. Okay, let's draw Pandu's hands. This is Pandu's hands like this, very thick Pandu. This is a very thick Pandu, okay? Okay, this is his hands, his biceps are very large. He just does hand exercises. He does a lot of pull-ups, push-ups and all of that. Very hard-working Pandu. Now, don't you think his hands are under longitudinal stress? His hands will have some cross-section. So, this is the cross-section of Pandu's hand. This is the cross-section of Pandu's hand. So, obviously, there will be forces which are acting along that cross-section. So, that force which is perpendicular to that area upon the area of cross-section is basically called as the longitudinal stress. In general, the symbol for stress is this sigma. Usually you will use the symbol sigma, but since this is longitudinal, I will put a subscript LONG that signifies it is longitudinal stress. That's it. This is the formula for the stress developed in a rod which is pulled or which is compressed. And what would be the unit of this? The unit will be Newton per meter square, as simple as that. Or you can also use Pascal. Both units work. Newton per meter square or Pascal. Dakshin, because this is a long class, that's why at 7 o'clock. Yeah, this is a little bit long class because I want to complete this chapter. And this chapter is simple, sweet and short. So we can finish this within 2 hours. Is that clear? So that is longitudinal stress. The second kind of stress is bulk stress or pressure. Many students ask, sir, what is the difference between pressure and your stress? Here is what it is. See, imagine I give you like a cube, okay? Imagine I give you like a cube. I apply force on this face this way, on that face this way. Will there be stress in the cube? Obviously yes. What kind of stress? Longitudinal stress. Should I call it as pressure? No. Usually longitudinal stresses are associated with solids because you can see the forces act in a particular direction. Okay, like when you pull a rod or you compress a column, you can see the forces are in one particular direction. Then for solids you define something called as the longitudinal stress. But for liquids there is no shape and size. If you take a blob of water, the forces are there everywhere. Here, 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 here. There is pressure everywhere. If you take a chunk of air, chunk of liquid, chunk of any fluid, there is forces on every side, no matter where you go. So the force which is acting per unit area is then called as pressure. Is that understood? So pressure is used for fluids. Okay, it's associated with fluids and it acts in all the directions, but for solids, generally the forces are in certain directions only. That's why you use the word stress. Is that understood, my warriors? Is that clear? So for fluids, you define something called as the bulk stress or normal stress, and this is nothing but change in pressure. Change in pressure on a fluid. That is called as bulk stress. So sigma BULK. Again, the unit is just Pascal or Newton per meter square. As simple as that. Change in pressure. You change the pressure, it deforms. You relieve the pressure, basically changing the pressure, it deforms. So that's what it is. Look at this solid, okay, or look at this fluid. You apply pressure from all the sides, the volume changes. You relieve the pressure, again the volume changes. So any changes of pressure changes the volume. That's what bulk or normal stress does. I hope this is clear. Now, very good, Isaac. The last type of stress, because I told you there are only 3 kinds of deformation, that is shear stress. I'll give an example. Okay, so here I have H.C. Verma book. Okay, this is my H.C. Verma book, and what I do, you can see a lot of pages arranged over here. Yeah, a lot of pages. I hold it below and I hold it on the top. I don't press it like this, but in fact I do this. I slide my fingers, I slide my hand. Do you see that the pages of the book slide over each other? Do you see the pages of the book slide over each other? You push it like that, the pages of the book will slide over each other like this. I hope you can see that way or this way. You can see that, left side or right side. So basically what has happened, it has skid over each other. There is sliding of layers. Whenever layers are sliding over each other, that is called as shear. That is called as shear. Example, another example. You take a knife. Okay, you take a knife and you are cutting your birthday cake. Okay, let me just show you another example. Okay, you take a knife and you are cutting your birthday cake. It's your happy birthday. Everybody is singing happy birthday song for you and you have no clue what to do. That's what happens. So you take this knife and you cut it through. So when you cut it like this, imagine what is happening. The layers are going to slide. So this layer which is there, this is going to slide down with the adjacent layer. So that is again shear. Yes. So sliding stress, correct Hemant, freaky. So when you cut it, the layer starts sliding, sak karke. So that's the reason why it is called as shear. Perfect. Hello Srashti, join in bachalo. Welcome Setu. So how do I define this kind of stress? It's simple. So it is nothing but the force per unit area. Look at this, a beautiful example animation of what sliding stress or what shear stress is. So again, the shear stress, I will put it, sigma shear is the force which is parallel to the area. Notice this, this is parallel to the area upon the area which is sliding. That's all. So force which is parallel to the area upon the area which is sliding. As simple as that. 3 definitions, done. Let's move to the next thing, which is strain. Stress is done. Stress is done. Let's talk about strain and then we'll quickly go to problems. Get ready. Strain. Strain is basically a dimensionless quantity which tells you how much fraction did the solid or liquid deform. It's a fraction which tells you how much deformation occurred. Strain can be both. It can be positive or negative. Strain can be positive. It can be negative. If it is positive, it has basically expanded. If it is negative, it has contracted. That is one thing. And understand, it is dimensionless. So no dimensions. Very, very important. There are no dimensions. Strain symbol is epsilon naught. It is nothing but a fraction. It can also be expressed in percentage as well. Okay. Now when I say a solid expanded by 1%, it means maybe the volume was 100, now the volume became 101. So the strain will be 1%. If the volume contracted from 100, it became 99, I would say the strain is minus 1%. So minus means it contracted, and 1% means if it was 100, it has now become 99. As simple as that. So that is what strain is. Epsilon naught is the symbol. So obviously, if there are three kinds of deformation, there will be three kinds of strain. Let's talk about it. Longitudinal strain. So you take a column, rod, compress, elongate it. So the length will change. So the longitudinal strain, okay, epsilon longitudinal will be change in length. Here I will put x divided by original length. So what is x? You can see that x over here. This is basically x and this is basically L. So what is L? It is original. It's the original length, and x is basically your change. Since this is meter, if you divide it dimension wise, there is no dimension. As simple as that. Okay, perfect. So longitudinal strain is the change in length upon the original length. That's what I have put it right over here. Hello Karu Prem Kumar, welcome aboard. Join in, and thank you for liking the video. It means a lot. Okay. Next, deformation. Bulk deformation. So we have bulk strain also. What is bulk strain? Okay, very easy. If you have a volume of fluid, solid, whatever, liquid, you change the pressure, the volume changes. So bulk strain, so epsilon bulk is delta V by V. What is delta V? It is change in the volume, because it is associated with bulk. Bulk means in general collective property, collective as a whole. So the liquid as a whole, so liquid as a whole, what's its volume and how much did the volume change by? That's all. So change in volume upon initial or original volume. That's what bulk strain is all about. So original volume was V0. So you can see some gap, that is the change in volume. Is that clear, my warriors? So Ajay, the class 12 revision timing will be 11 o'clock tomorrow for the marathon sessions for CBSE term 1. Okay, very good, Noreen. Third type. What is the third type? Shear. Remember I told you about shear sliding. I showed you H.C. Verma book sliding, the layer sliding. So if one layer slides with respect to the other layer and it displaces by x, the area slides by x because of this force. There is an angle which is created. The distance between the layers is L. So let me mark this. So this is basically your sliding layer. This is your sliding layer. Okay, this is your sliding layer. What is this? L. This is basically distance between the layers. This x, what is this x? It's the amount of sliding. It's the amount of sliding. Okay, or basically shear, you can say. This phi, theta, whatever you want to call, you can call it as the angle of shear, and then you define the dimensionless quantity as x by L. How much did it move for whatever distance between the layers? So the shear strain, remember epsilon is strain, this is shear strain, is x by L, which is also tan theta by geometry, or tan phi, whatever you want to call it, tan phi. You can see that. And if theta is or phi is small, then it is approximately phi in general. Okay, because this is very, very small angle in general when phi is very small. That's what you should remember. Is that clear? Yeah, no problem, Roshni. I know usually my classes are at 7:30, but today I conducted at 7 o'clock. Reason being I wanted to finish this chapter. Yep. Okay. Gaurav, today I will complete the theory part and the basic problems part, but we'll have one more class on this for just problem solving. Is that okay, Gaurav? Yep. Yes, Remo, this is the new chapter. Yes. Okay, SHM also theory and basic problems done. We'll have problem solving sessions on SHM. My aim is to make sure that we cover all the basics, and simultaneously as revision we'll conduct problem solving classes. Alright, cool. Chalo. Thank you for all the love. Moving on. So that was X by L, which is fine. Let's start solving some questions coming up on your screen. There is a spring which is stretched by a force. The resultant strain produced in the spring is volume, shear, tensile, none of the above. Hi Jarup. No problem, Chandran. You can start from beginning even in a live class. So all those of you who are joining in right now at 7:30, please rewind the session, catch up to the current topic even at 2x speed, or even if you continue live, you can still watch it. No problem. Okay, great. So what kind of strain is produced in a spring which is stretched? Some of you are saying shearing. Okay, thank you, Vignesh. I'm so happy that you are happy about me, and so it means a lot. All right, trustee, come on. I hope you have coped up. All right, come on, my warriors. What do you guys say? Is it volume? Yep. Is it C? Well, the correct answer is actually B. I'll tell you why. No, it is not C. It is not tension. A lot of students make this mistake. That's why I deliberately put this question. Students think, sir, spring, sir. Obviously, it is stretching, longitudinal tension. Tension is there, sir. Correct. But the tension is not there in the spring as such, the way you are thinking. It's actually the tension in the string which is connected ahead. Actually, what happens? The spring which is coiled, the layers twist with respect to each other. Think of a spring as multiple discs, one over the other. This is a disc, okay, like this. Then let's say another disc over it, okay, then another disc over it, like this. So there are multiple discs, over it, okay. Now, when you expand a spring, what happens is each layer with respect to the lower layer turns relative to it. So when you expand, it basically twists. That layer twists, and that's why the spring appears to increase the distance between the two adjacent coils. This distance increases. So when it twists, okay, it turns the distance, it moves away the spring coils away from each other. That's what happens. Observe the animation, you will make a sense out of it. Look at this. These are turns, these are sections. Think of like small slices. Each turn will, slide with respect to each other. That next turn will slide with respect to each other. The sections of that coil twist with respect to each other. So there is sliding action. The slices twist. So that's why it is shear. A lot of students make that mistake, but I hope now it makes sense. Look at the coil's cross section. There is a thick coil. That coil's cross section is turning. That is turning. So that is turning. So that's why the distance increases. That's what happens. Is that clear? Okay, moving on to the next one. One end of a uniform wire of certain length and weight W is attached to a point on the roof, and another weight is suspended from it on the lower end. If S is the cross-sectional area of the wire, the stress in the wire at a height of 3L/4 from its lower end is going to be. Okay, I know, Hemant, it's a beautiful question. Let's try and solve this. So let's say this is the rigid end. Let's say this is your wire. Okay, maybe this is your wire. Okay, and you have some weight which is attached down over here, which is in the roof, and the weight Wn is suspended from the lower end. Okay, so weight Wn is suspended from here. This is weight W. The question is at a distance of 3L/4 from its lower end. So 3L/4 means here. So at a distance of 3L/4. Question is, what is the stress over there? Let's figure this out. Now if you look at this cross section will have some tension force. Correct? There will be some tension force. What will be the value of the tension force? Jaya Govind, no bacha, waves chapter will come in the end. Not now. We'll first do fluids after this, then we'll do thermo, and then we'll do waves. Is that okay? So this tension is balancing something. What is it balancing? Think about the mass which is hanging below it. This is the mass being supported. Correct? This is the mass being supported by it. Okay? So what is the total mass of this system which I have enclosed over here? It's not just W1 but also this much part. How much is the string's mass over here? What is the mass of this much part of the string? For this much part, what's the mass or what's the weight? If this much is weighing W, how much will this much weigh? Remember, the total length is L. Total length L, I'll write it over here. For total length L, it is W. So for 3L by 4, what is the weight going to be? Think about it. Obviously, it's proportional. For length L, it is W. For half length, it will be W by 2. For 3L by 4 length, what will this question mark be? It will be 3W by 4. So hence, this weight is just going to be 3W by 4. Isn't that right? So what is tension supporting? Tension is supporting 3W by 4 plus the W1. This is the weight which it is supporting. Perfecto. Now, the question is not that, the question is stress. So the stress value, okay, so the stress value for longitudinal part is nothing but going to be the tension divided by the area. So what is the tension? It is 3W by 4 plus W1 upon what is the cross-sectional area? S. So that's it, divided by S. So 3W by 4 plus W1 divided by S, which is option C. Is that understood? Very good, Arun. Very good. Kanmani, very good. Excelente. Proud of you, bachalo. Yeah, that's the answer. So you will see at different points, the tension will be different, the stress will be different. There will be a beautiful question coming up towards the end of the class. So wait for it. This has laid your foundation for the next question which will come towards the end. Okay, so wait for that end question. All right, so moving on to the next concept, Hooke's law. Zayed, you should be regular, or else you will start developing backlogs and you will start losing interest. So make sure you are regular, Zayed bacha. See, we just spoke about stress and we spoke about strain. Now, here is what I want you to understand. Stress, which is sigma, and strain, which is epsilon, this is strain, they are very much related to each other. If there is more stress, more force per unit area, it will deform more. More the deforming forces, more the strain, more the changes in the dimension. So Hooke observed that for most of the bodies, okay, within elastic limits, the sigma is proportional to epsilon. Is that understood? And that also means sigma by epsilon. This was what was observed experimentally. This is by experiments by Hooke. And that ratio is a constant. That constant is called as the modulus of elasticity. Now, why do I use the word modulus? Does anybody know about this? Why should I use the word modulus? Zayed, try to manage it, bacha. Try to finish your homework in the night or during other days. Make sure your focus is on JEE or NEET, whatever competitive exam you are giving. Homework will come. Other students also have homework, but you need to manage time. Now, why is it modulus? Modulus means positive. The reason why I said modulus is because this guy over here can be positive or negative. Remember strain, when if it is positive, it expands. Strain is negative, it contracts. So, irrespective of that, this constant is positive. That means actually speaking, we should put a modulus symbol over here. Yep, that's what it is. Okay. So remember, modulus of elasticity means it's a positive number. Doesn't matter whether it is expanding or contracting, the ratio remains the same for both expansion as well as contraction. That's what it means. That's all it means. The ratio remains constant irrespective of whether you expand it or contract it. Hi Abash, welcome, join in. Let's look at 3 different moduli. Why 3 different moduli? Because I just told you there are 3 different kinds of deformation. So obviously 3 stresses, 3 strains, 3 moduli. So what do we have? Let's talk about it. Modulus of Young or Young's modulus. Why? This is associated with longitudinal deformation. Longitudinal. If you ever get confused, think of a young guy who is very long. What will you think? Think of a young guy. Who is a young guy? Bacha type. This is bacha. Bacha means, okay, young guy. And he is very long. This is Young's modulus. That's how you can remember. Young's modulus? Yes. Longitudinal. That's how you can remember it. Very good. So, this Young's modulus will be longitudinal stress upon longitudinal strain. So, strictly speaking, this is that force which is perpendicular to that area. Remember, stress was force by area. I just told you force which is perpendicular to that area. Upon strain, strain is this change in length upon the original length. That's what you will get this as. Okay, beautiful formula. Now you don't have to remember this one, but any modulus is stress by strain. You know stress is force by area. You know strain is change in length upon original length. That's all you should remember. Very good. Oh my god, that was quick use of symbols. Bhagwan, I think I have seen it and I have also informed the team. Just hold on. I'll just make sure that it gets resolved within this week. Okay? Yes, Bhagwan sir. All right. So, fair enough. Now, here is the next thing that I want you to realize. This force which you apply, believe me, is basically going to be related in a very special way to this delta L. Observe this. Let me rearrange. And I will show you one very interesting thing. Okay, let's move this let's move this over here. So it will become y into delta L by L is equal to F perpendicular by area. So take that area there. So it will become y A by L into delta L is equal to that F perpendicular. Flip it here. So I'll make this as force, which is YA by L. Delta L is extension. Now tell me, Y is a constant, A is a constant, L is a constant. Force is some constant into extension. Is there a deja vu moment? Is there a deja vu moment? Do you remember something? Think. Shanu, don't worry, just leave a comment or just ping me on Instagram. I'll help you. Okay, I'll help you find the micro course. Don't worry about it. Look at this. This is a deja vu moment. Spring force is some constant into extension. This term over here is like spring constant. This is like spring constant. Very, very important. So you should remember this value. Equivalent spring constant is YA by L. Remember this, okay? Apart from remembering Young's modulus is stress by strain, remember equivalent spring constant is YA by L. Very good, like spring forces. Perfect. YA by L, YA by L. Keep saying this couple of times, 10-15 times. YA by L. YAL. Okay, remember YAL or YA by L. Just keep on saying it. Okay, now one last thing. What is this Young's modulus? Young's modulus depends on whether it is aluminium, whether it is steel, whether it is stone, whether it is brick. So it depends on that material. Okay, so it completely depends on the material. Just to give an example, the Young's modulus for steel is around 2 into 10 to the power 11 Newton per meter square. Just an example. 2 into 10 to the power 11. That's a huge value of Young's modulus. So if the Young's modulus is more, you need more stress to produce that deformation. That's what it means. If Y is more, you need more stress to produce that deformation. It's very difficult to deform it. If it is less, it's very easily deformed. Perfect. Young's modulus, stress by strain, but everything longitudinal. Pranish, how about this? Leave a comment after the session ends. I'll definitely help you, or contact me on my Instagram handle, Shreyas_Vedantu. Okay? Fair enough. Next, bulk modulus. Come on, everybody knows the formula for bulk modulus because all the formula are similar. So, bulk modulus. Let me just put it up over here. Bulk modulus will be what? Bulk modulus will be nothing but, okay, here we have it, bulk stress. Okay, bulk stress divided by the bulk strain. And we all know the bulk stress is nothing but change in pressure, correct? It is change in pressure. The bulk strain is change in volume by original volume. That's what it is. But there is one small catch when you write, when you write this formula. Just imagine, I'll give an example. If you compress something, is delta P positive or negative? You help me out with this. If you compress something, the change in the pressure, have you increased the pressure or have you decreased the pressure? So is the delta P positive or negative? No, CJ Rahul, braking has got nothing to do with Young's modulus. You will see it in a bit. Okay, that's completely different. A lot of people associate Young's modulus with braking. That's wrong. Okay, so if you compress something, delta P is positive, but delta V is negative. Correct? Change in the volume is negative because it has compressed. Volume has decreased. But we know B is a positive number. How do you make B positive? Just put a minus sign. So always in this formula, you will see a minus sign. That's how you are going to remember it. I'll give you another example. Imagine another example where it expands. If it expands, then delta P will be negative because pressure will become less. Change in the pressure is negative, but change in the volume will be positive. Negative by positive, negative. To make it positive, put a negative sign. So both cases, if you put a negative sign, you will be safe. Understood, my warriors? Is that clear? Why we have put that negative sign? A lot of you might have been wondering. So that's the answer. Normal stress by volumetric strain. Bulk stress by bulk strain. As simple as that. Let's start solving some questions. But before that, the last modulus, which is also called as the shear modulus or rigidity modulus. Shear, rigidity mean the same thing. Okay, so shear modulus, okay, shear modulus or rigidity modulus, one and the same thing. Eta, okay, some books also use the symbol G, okay, some books also use the symbol G. So up to you, whatever symbol you want to use. You look at the question, they won't confuse you with symbols, they will give you the shear modulus of aluminium is this much. So they will express it in words so you don't have to break your head. So the shear modulus G or basically eta, whatever you want to call it, is shear stress upon shear strain. Shear strain. And shear stress is that force which is parallel divided by area, and shear strain, I just told you, it is just phi or basically x by L, whatever you want to call it. So that's the formula for rigidity modulus. Very interesting. Force upon the area which is parallel to the surface upon the angle of deformation, or you can also call it x by L. That's the same ratio, opposite by adjacent side. Okay, perfect. Ready for solving some questions, my warriors? Geared up? Okay, because unless you solve some questions, you are not going to get some idea. Very good, Aditya. Very good, everyone. What is GGECO? Rigidity modulus or shear modulus? Okay, Dinesh? Cool. Let's solve some questions. The Young's modulus of a wire of certain length L and radius R is Y Newton per meter square. There should be meter square, guys. Okay. Okay. If the length and the radius are reduced to length by 2 and radius by 2, then the Young's modulus of that particular wire will be how much? Y by 2, Y, 2Y, 4Y. Let's see how many of you can do this within maybe 30 seconds, not more than that. Let me put a 30-second timer. Come on, my warriors, I want all of you to answer this question. The timer has started. Somebody is saying C. I don't know. Jairup also saying C. Aslam, no. The crash course which is starting today does not have recorded classes. It will be live classes. But if you miss a class from today, then the recording will be available for you later on. Okay, so it's a fresh batch starting today. And if you missed any of the class, even today's class, you will get the recording even today or tomorrow. Okay, till the end. Well, the correct answer is actually B. Very good, Hemant. A lot of you made that mistake. Very good, Harita. Very good, Kavani. See, Young's modulus is only dependent on the material. Many of you thought, sir, Young's modulus is force by area divided by length by change in length by original length. Oh sir, area change, length change. Yeah, if these two change, now the force will change. Young's modulus will not change, it only depends on the material. Material is still the same, only length has changed. Understand that. Many people make that mistake. Diva, I just conducted a strategy session just 1 hour back. Watch it. Number 1. Number 2, I've already mentioned my 12th standard classes will be tomorrow onwards before the marathon. I've already conducted so many CBSE sessions just for you. So make sure you watch that strategy session, okay? And be there tomorrow at 11 o'clock. Alright. Hello Nitin. Here is the next question. If stress is numerically equal to twice of Young's modulus, the elongation will be how much? Very good, Diva. Don't worry, I will be there. Okay, just study for now till the night. In the morning, just be there in the session. I'll take care of everything. Okay, and just follow whatever I'm saying. We are with you. All right. Don't worry, Diva. Okay. What do you think is the correct answer? Let's put up 30-second. Oops. Wait a minute. 30-second timer just for all of you. Let's see how many of you can get this within 30 seconds. Again, this has gone to 59 minutes. My goodness. Okay, just there we go. 30 seconds. What do you think? If stress is equal to 2 times of the Young's modulus, what do you think the elongation will be? Yes, Selva Kamantan. NCRT. I have given you what and all you should solve. Just watch my strategy sessions. Definitely. And if you still have some doubts, please let me know. Diva, I'm not sure if school will be so beneficial. If you think it is worth, then please go. But if you think it's again going to be time pass, and if you want some other input, then I would suggest watch my session. But if you think, no, I want to attend school plus my session, then you can watch my recording. That's the only other option left. Well, the correct answer is twice the original length. Okay, how many of you got that? Very few of you got it. Some of you said B, some of you said C also. I'll tell you why. Stress is given to be twice of Young's modulus. That's what is given. Now we all know Young's modulus is stress by strain. Now here, according to the question, stress is twice of Young's modulus. So y goes, so therefore 1 is equal to 2 by E. So therefore epsilon is equal to 2. When this is 2, what does it mean? It means the change upon initial. So essentially what it means, the change is 2 times of initial. So it is twice the original length. Compressibility, Balaji, is 1 upon bulk modulus. So if you have seen the word compressibility, okay, if you have seen the word compressibility, it is 1 by the bulk modulus. That's it. So that's all. So if it is more compressible, okay, so if it is more compressible, it has less bulk modulus. If it has very large bulk modulus, very difficult to compress. That's what it means. Aslam, the crash course will be in English. Okay. Okay. Next question coming up on your screen, and here it is. Great. Okay. 2 parallel and opposite forces, each of 5,000 Newton, are applied tangent to the upper and the lower faces of a cubical metal block of side 25 centimeter. The angle of shear is how much? The shear modulus, I just told you, right? They always give you the shear modulus in words. And this is what it is, 80 gigapascal. So the question is, what do you think is the angle of deformation? Let's see how many of you can get this really quick. So let me just draw the diagram just for you. So here is our, deformed body, and I think this is the angle which I want to calculate. Here is where I have applied the force on that particular area A over here. We all know G is sigma by epsilon. Sigma is force by area. Epsilon is nothing but tan theta or just theta. So the question is, what is theta? So theta will be F by AG. Theta goes up, G comes down. So F by AG. So let's start substituting. What's the force? The force is 5,000 Newton. So 5 into 10 to the power 3. What is the area? Achha, the side is 25 centimeters. So what will be the area of cross section? 25 centimeter into 25 centimeter, which is 25 square into, this is centimeter square, so 10 to the power minus 4 meter square. So I'll just put 25 into 25 into 10 to the power minus 4. This G is 80 gigapascal. So 80, so 80 giga, kilo, mega, giga. So 10 to the power 3, 10 to the power 6, 10 to the power 9. So into 10 to the power 9. Fair enough. Now let's see what and all gets cancelled. This 5 and 25. So this will become 5. So 5 into 25. Okay, let's get rid of it later on. This 0 and 10 to the power 9 will become 10 to the power 10. This 10 to the power minus 4 and 10 to the power 10 will become 10 to the power 6. This 10 to the power 6 and this 10 to the power 3 will become finally 10 to the power 3 over here. Now 5 into 25, 125. 125 into 8. What is 125 into 8? That's 1000, right? So this will become 1000 into 10 to the power 3, which is 10 to the power minus 6. What is this theta? Radians. That's all. So I think 10 to the power minus 6, here we have it. Option C. Perfect, Allah. Very good, Uma Devi. Very good, Kanmani. Okay, definitely, Shanu. I'll check it out. Definitely. So Selva Manikantan, I'll do one thing, bacha. Because I'm conducting a 11th standard class, can you do one thing? Just post your comment after the video ends. I'll definitely respond to you. Just leave it over there. I'll definitely help you out. Okay? Cool. All right? Yeah. Great. So that's the answer. Now, here is the next thing. Very good. A massive rod hangs from a ceiling as shown. Find the elongation in the rod when it is in equilibrium condition. Here is it. Very interesting question. The thing is, many students fail to realize that the rod itself has mass. So its own weight is causing the expansion. It's not like the rod has a mass attached below and you have to just do weight by area that will give you stress and that will give you the change in the length. No. The problem is the own weight is causing some deformation. Now there is another problem. Do you think there will be equal stress throughout the rod? Yes or no? Yes or no? What do you think? The same stress will be here, 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 everywhere? Or do you think it will be different? Let's talk about that first because it's not so easy. It will be same? Well, then if it is same, then most of you are wrong. Because I just told you that I'm going to do a very interesting question after some time, and here is where that concept comes into play. Think about it. Over here and over here and over here, the tensions will be different. I'll give you the best way to visualize this. There is a Pandu, he's holding like this, and another Pandu is holding his legs, okay, and then another Pandu is holding this guy's legs, okay, and then another Pandu is holding this guy's legs, something like this, okay, beautiful, that's how it is. If I give these numbers 1, 2, 3, 4, do you think all the Pandus will have the same tension in their arms? Will they have same tensions? Hemant, I can't comment on other coaching, but you know, from what my experience is, it's not that great. Okay, so 1, 2, 3, 4, what do you think? It will not be same. Obviously 1 will be highest, then 2 will be next, 3 will be less, 4 will be even less. Same thing is happening here. The uppermost mass is holding the entire mass below. So highest tension. So T1 is very large. T2 is normal. T3 is even less. So the tension changes within the rod. If tension changes, will stress be constant or not constant? Will stress be constant or not constant? Obviously it will not be constant. If stress is not constant, strain won't be constant. If strain is not constant, deformation will not be same. And if deformation is not the same everywhere, how can you just say it is mass by area and whatever nonsense? No, right? You cannot. So I think we need to first of all break the rod into small parts. Think about it. Each element, so basically what I'm going to do, I'm going to consider each element. Okay, I'm going to consider each element of the rod. I'm going to see how much elongation is there in each element. Each element's elongation can be added, dx, 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 and I will get the total elongation of that rod. Did you guys get it, my warriors? Why I'm going to make use of calculus now? Yep, this is a question on calculus. It's not so straightforward. Okay, everywhere the deformation is going to be different. So let's just forget about the options and focus on solving the question. This is a beautiful question. So elongation of a rod due to its own weight. That's what the question is. Okay, so it's basically elongation due to its own weight. And the reason why I'm dividing it into elements is because, you know, the stress is not constant. So I'm just going to take some element right over here. Okay, this element, let's say, is at a distance of x from the bottom, and let's say the width of this particular element is dx. What's the width of the element? Dx. So this is basically your original, it's your original length of the element. At a distance x, obviously there will be some tension, right? At a distance of x, there will be some tension in that particular element. So if I ask you, okay, if I ask you, what is that tension, okay, over here? What is that tension which is over here? Why do I need the tension? Because I need to calculate stress. Then think this way, the tension supports the weight which is there below, supports the weight below, just like the problem which we solved some time back. And how much weight is there below? Think like this, for length L, the weight was capital M into G. For length L, the total weight, okay, the total weight was M into G. For length X, how much is that weight? For length X, how much is that weight? Think carefully. Think. Who said only 30 days baki hai? Somebody has fooled you. Only 30 days are remaining. There are more than 30 days remaining. Chill. Okay, and we are going to complete all the syllabus. Number 2, I am going to come up with one shots very soon. Just give me 2 weeks maximum. Yeah, 2 weeks of time. Don't worry. Okay, aspirant. Yep. So by the way, if mg is for length L, what do you think is the weight for x length? Obviously, it's mg divided by L into x. Force or weight per unit length into the length. Mg into x divided by L. Everybody agrees with this fact? Yep. Very good. Very good. So once you understand this, you know what is the tension. Tension is the weight which is supported below, and the weight which is supported below is basically mg by L into x. This is what the tension is. If you know the tension, you also know the stress, because stress is tension by area. That means it is mg x by LA. So that's what the stress is. Perfect. Once I get to know the stress, I think I can find out everything else. Use the definition of Young's modulus. Young's modulus is stress by strain. Oh, I don't know the strain. Let me think about it carefully for some time. What do you think is the strain in this element? Many students write, sir, I know what is the strain. It is dx by x. Guys, you are wrong if you are thinking it is dx by x. I'll tell you once again. What is strain? Change in length upon original length. What is the original length? Is it x? Obviously not. In fact, the original length is dx. Observe carefully. For that element, it has a length dx. So actually speaking, denominator is dx. Then what is there in the numerator? In the numerator is the change in length of dx. In the numerator, you have the change in length of dx. So let me assume that to be dl. So what it means is that that element which had a length of dx, it has changed its length by dl. So every element changes length by dl, 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 dl. If I add all those changes, I get the total change in the length of the entire rod. Is that now clear, my warriors? Think about it. Is that perfectly understood? Cool. Let's go ahead. So let me substitute everything over here. Sigma is mgx by La. Epsilon is dl by dx. Okay, I don't need this anymore. Rearrange. I think dx will go on the top. I'll just rewrite it. So mg by, okay, so we have La into dl. Dx goes on the top, x and dx are right over here. I think I can shift dl there, y below. So it will become dl is equal to mg by Lay, and here we have x and dx. I think I know what to do next. You can see it is in the integrable form. If I put integral symbol here and here, I can remove this outside the integral because all of them are constant values. That's it. So integral symbol on both sides, integrating both sides. I just have to substitute the limits. So value of x will start right from the bottommost element till the topmost element. So all the elements from 0 to capital L. This dl is 0 to small l. What is this? This is your total extension, small l. Is your total extension. This L is the length of the rod. Is the length of the rod. Understand? So here adding the small extensions, these are extensions of each element. I will get the total extension. So let's see what do I get. Okay, everybody fine till this point? Let's see what do we get. I'll just erase this, I no longer need it. dl's integration from 0 to L will be L, and then I'll put 0, so L minus 0. mg by Lay, integration of x dx. X dx integration is x square by 2, correct? X raised to 1 plus 1 by 1 plus 1. So x square by 2. So it will be nothing but capital L square by 2 minus 0 square by 2. Perfect. This is 0. L and L cancels. So I will get mg, one of the L goes here, and 2ay, and this is L. So this is our final answer. Hi Salvan, good evening bacha. Is that clear? So what a beautiful question on integration and its application. And it's very important to understand the flow of thought. We started by saying stress is not same because tension is different. The first thing was to identify tension is different by feeling. If you felt wrong, that's it, you go wrong. Then we understood, okay, every element will have different strains. And then I used the definition of Young's modulus and I substituted everything. And this rest is maths by rearrangement. I integrate it with proper limits. That's it, you get the answer. Perfect. That's the answer, mgl by 2ay. Perfect. Very good, Aditya Verma. Moving on to the next part. We all know that a stretched bow has some energy stored with it, right? Any deformed body tends to regain its original shape. So it has some energy stored with it, potential energy. But do you think plastic bodies have energy stored with it? Let me know in the chat box. Plastic like clay, cheese, anything which you deform, leave it, it stays there. Do you think plastic bodies have energy stored with it? No, right? Elastic bodies have stored energy within it. So that's why I call this energy as elastic potential energy, like in the spring. So a spring which is deformed has elastic potential energy. Plastic bodies do not have any energy stored in them. So we can find that out. It's not that difficult. And I'll tell you how to find it out. I think I just told you that a rod, a body which is elastic, is very much similar. It's very much similar to nothing but a spring which has been stretched by X. I just told you, a spring of natural length L and constant K. It has been stretched by X. And I just told you the equivalent spring constant is nothing but YA by L. So what is the energy stored in a spring? What is the energy stored in a spring? U. It was nothing but half K, whatever is the spring constant, into extension square. Correct? So how about using that same formula and finding how much energy is stored in a rod or any body which is deformed? That's it. So the energy stored will be half YA by L into X square. That's it. That's the answer. As simple as that. So the elastic potential energy stored in any deformed body is half, okay, equivalent constant of spring into X square, extension square. Equivalent spring constant is YA by L. As simple as that. Very good. Now there is another way of writing the same formula, and that's what I want you to see that. Okay, let's see how we can write the other way of the same thing. Now remember that Young's modulus, correct? Young's modulus is stress by strain, and stress was force by area, correct? Stress was force by area and strain was X by L. Let's somehow use all these things. Probably I might get something. Let's try this out. So YA, okay, let's just substitute both of these things over here. So I'll get Young's modulus is force, and then we get by area and change in length upon original length. I think I have YA and L below over here. Okay, let's do one thing. So YAX divided by L is F. Wow, very good. So YA by L into X is F. So here is what I'll do. U is half, okay, YAX divided by L. I've just taken it aside, and one of the X is separate. Fair enough. But I know one more thing. This force divided by area is stress. This YAX by L divided by area is stress. So if I divide this with area, I know in the next step, if I divide this with area, I'm going to get stress. But to maintain and preserve the equality, I have to multiply by area. I have to multiply by area. Correct? One last thing. If I divide X with original length, I get strain. X by L is strain. So to preserve the equality, I need to multiply it by L. Fair enough. Now see what happens in the next step. It will become half. This thing is force by area. Force by area is nothing but stress. X by L is nothing but strain. Area into length. What do you think is this? Come on, my warriors. What is area of cross section into length? Isn't this volume? As simple as that. So can I just say stress into strain into volume? Interesting, right? That's a very interesting formula. This potential energy is half stress into strain into volume. As simple as that. Thank you, unforgettable love. Yeah. So some books also write energy per unit volume is half stress into strain. That's also fine. Energy per unit volume is half stress into strain. Yeah, it's the same thing. So this and this, both formulas you should remember. Okay. This is easy. K is YA by L. If you remember that, it's very easy. This is also very easy. Half stress into strain into volume is total energy. So one and the same thing. So I put that formula just for you. Energy density it is called. What is this term called? It's called energy density. So it is in joules per meter cube. We can notice the unit. This is energy per unit volume. It's also called as energy density. How much energy is there per unit volume? Perfecto. Excellent. Let's go ahead. Shall we do some questions based on this? Okay, there we go. Now this is a beautiful simulation of elastic energy. Look at this. There is a rubber band. There are two matchsticks. You can try it at home with parental supervision. Yeah. You stretch that rubber band. You pull that rubber band. Leave it from one matchstick. There is elastic energy stored in it. That matchstick goes and hits that matchstick. That's it. it produces heat, sparks, energy. So where did that heat energy come from? It has come from, that sparks, that ignition has come from the elastic energy. What a beautiful way of showing elastical energy. Interesting. Okay, energy conversion from elastic to sparks and then heat and light and all of that. Let's do some questions. Here you have it. There is a steel wire of 1.5 meter length, area of cross section 1.5 millimeter square. It is stretched by 1.5 centimeters. Then what is the work done per unit volume? Let's see if you can solve this question within a minute, not more than a minute. Okay, I'm giving you 1 minute. Yes, it got sheared off over there. Yeah, that was there. Let's see how many of you can do this. Come on, bachalo. Yes, you can try it at home, but with supervision. Don't try it alone because it can be dangerous. Yes. All right. Yeah, the matchsticks are shear, but the rubber band was longitudinal. Hi Molesh, looks like you're late. Okay, 25 seconds to go. Figure this out. The wire's length is given, area of cross section is given, extension is given, Young's modulus is given, work done per unit volume means energy stored per unit volume. As simple as that. Come on, let's do this. Hardly 10 seconds to go. Come on, my warriors. I know few things are not given, but you can rearrange the terms and you can still get it. And the time is up. Let's do this. This work done per unit volume just means energy density, which is half stress into strain. But stress is not given, strain can be calculated because x is given, change in length, and original length. Stress is not given, but I can do one small trick. Young's modulus is stress by strain. Therefore, stress is Young's modulus into strain. Young's modulus is given. So how about putting that over here? So this will be half, instead of sigma, put it as Young's modulus into strain into the strain. So this will become half Young's modulus strain square. Correct? So now start solving. Half Young's modulus is 2 into 10 to the power 11. Strain, change in length, which is 1.5 centimeters. So 1.5 into 10 to the power minus 2. This is whole square. Okay, upon original length. Original length is 1.5 meters. You can see so many things will get cancelled. This to 1.5, 1.5. Fair enough. So what do we get? 10 to the power 11 into 10 to the power minus 2 whole square is 10 to the power minus 4. 11 minus 4, that's 7, right? So 10 to the power 7. So is it there? Yep, it is. That's the answer. Unit wise, it is joules per meter cube because this is energy density. Very good. So Jairoop, the questions could be similar for mains and NEET, but still I would say it is a 70 to 80% match. 70% of the questions will match, but those 30 questions will be slightly higher than JEE Mains. Okay, the 20-30% approx. All right, cool, very good. That's the answer. I hope many of you got it. Next question coming up on your screen. Two wires of the same diameter, same material. The length are L and 2L. Force is also same. Ratio of the work done in the two wires will be. Not work done per unit volume, just the total work done. Very interesting. Let's try to understand and decipher what is given. Two wires of the same diameter. The meaning of same diameter means same area of cross section. The meaning of same material means same Young's modulus. Okay, same Young's modulus because material property decides Young's modulus. Lengths are different, forces are also same. So F is basically also same. So the question is work done. Work done is basically the energy stored, elastic energy. So let's try to see if there is a formula for that. What can we do? Think. Work done, which is energy. I think I can use half into, stress into strain into volume. Well, I can do that. Or I can probably somehow rearrange it in some different form, like it was half k into x square. K is nothing but k is nothing but ya by L. Remember, that was the equivalent spring constant into x square. Now let's see what else can we do. Oh, there x is not given. X could be different because lengths are different. Achha. Can I do something about it? Because x could be different, right? So how about using another trick up my sleeve? So y is force by area by change in length upon original length. If you realign this equation, which is y is F by ax into L, rearrange it further. So x comes on the top, it will become FL by AY. Interesting. So I know what is x. X is FL by AY. Put it over here and see what happens. It will become half YA by L, x square. So F square, L square by A square, Y square. See what and all gets cancelled. One Y gets cancelled, one of the area gets cancelled, one of the lengths gets cancelled. So I'm just left with half F square into L by AY. Out of these terms, observe, F is constant, F is same diameter, same area is same material, same Young's modulus. So can you quickly observe potential energy stored is directly proportional to the length? Potential energy stored is directly proportional to the length, and this energy was nothing but the work done. I've just mentioned it. So basically the work done is proportional to the length. So hence W1 by W2 will be L1 by L2. What is the lengths ratio? Lengths are L and 2L. So therefore it will be L and 2L. That means 1 by 2. Hence the answer will be option A. Done, done. Very good, Aditya Verma. Looks like you are quick. Very good, Arun. Hemant, no, it's not D. Unfortunately, yes, Selvaraj, it is option A. So beautiful application of energy concept and the definition which was there, Young's modulus. You have to just play around with it. That's all. Hello, Kaniska. Welcome. Join in all the new warriors. In case you have missed the class and you forgot that the class is there, or you're very new to the channel, first of all, hit the subscribe button. Join the only English medium channel in the country for engineering entrance, Kvpy entrance, board preparation, everything on this channel. The only English medium channel for all the English medium students. Go ahead, join in. Okay. Now there's a beautiful curve that we are going to see. Stress and strain curve. Beautiful. Okay. It's amazing to notice it. Now, imagine. Okay, I don't have anything to break, maybe. But yes, I think I have found something that I can break. And I'm going to show that to you. Wow, I have a almost worn out rubber band. Can you see it? I don't know. Yeah. Let's see. This is almost like elastic, but still it shows some plastic property beyond a point. Stress strain curve. Stress is what I apply, force per unit area. Strain is the deformation. So force per unit area on one side and the effect, which is the strain, the deformation on the other side. Arun, this is also for ICSE board because all the boards have the same portion. Obviously, everybody is studying Newton's laws, everybody is studying, rotation, everybody is studying the same things. It's not different. It's just the boards are different and the manner in which they cover the syllabus is different. But at the end of the day, you are studying the same thing. Okay, Arun? Don't spam, by the way. Now, what I'm going to do is I'm going to apply some force. If I apply stress, what is happening, my warriors? If I apply stress, what is happening? Strain is increasing or decreasing? Come on, let me know in the chat box. Come on, my warriors. If I apply stress, strain is increasing or decreasing? And is the stress proportional to the strain? Yes or no? Come on. More stress, more strain. More stress, more strain. Right? Now, if I leave the stress, it comes back to its original shape. I apply stress, deformation, more strain. Leave the stress, strain goes off. So, as stress increases, strain increases. As stress relieves or goes away, strain also goes away. More stress, more strain. No stress, no strain. Comes back. Perfect. Now, I keep stretching it. I think beyond a point, if I stretch it, I will stretch it. Oh my god, now I leave it. I think the length has increased. I don't know whether you can see it, the length has increased. I can feel it. Oh my god, it even broke. After a point, if I keep stretching it, oh my god, this broke. I don't know whether you can see it. And if I leave it now you have a longer rubber band. Now you have a longer rubber band. Okay, you have a longer rubber band. Yeah, so what has happened beyond a point? When you keep stretching it, it becomes plastic in nature. It shows more plasticky behavior. When you stretch till a limit, then it comes back. But if you put so much force, but don't allow it to break, and you leave it, it will deform permanently. It shows plasticky behavior. So that point till which it shows elastic behavior, and after the point when it converts into plastic, that point is called yield stress or yield point. What is it called? Yield point. Y-I-E-L-D. Yield point. So what is yield point? After yield point, the elastic behavior converts into plastic behavior. No unforgettable love. This is not my wife's hairband. Okay, she doesn't use this band. I mean, I get pretty decent salary. I think I can afford her much better hairbands. I'm not touching my wife's makeup kit. Yeah, this is the hairband which was there in my drawer for some reason. I just found it in my stationery drawer. Okay, great. Okay, chalo. If I use this kind of hairbands for my wife, I'm pretty sure she's going to run away. All right, cool. Now, if I apply more force, let's break this. Oh, there it goes. It breaks. Tuck. Breaking point. So every material has its breaking point. We have two things over here. You can see that. It just broke. Perfect. So that is what the stress strain curve is. I just showed you practically how stress strain curve looks like by demonstration, and now we are going to actually see it on this board. So you pull it, it becomes weak and it finally breaks. So if you look at the graph, let me show it to you right over here. See, pull, tuck, break. This is how the stress strain graph looks like. In this region, do you see in this region, the stress increases, strain increases. Do you see this point? What is this called? Yield stress. What is yield stress? The maximum stress till which it will show elastic behavior. Beyond this point, if you go, this is plastic zone. What is this? Plastic zone from B to C. If you leave it, it will be deformed. If you leave it, it will be deformed. Perfect. And do you see there is a maximum limit till which it can go? That maximum limit is ultimate strength. It is the strength of that material. It's the strength of that material. Look at that. Strength of that material. That's it. After that point, it breaks. Tuck karke. Also notice, this graph has a slope. What do you think the slope will represent? What do you think the slope will represent? Come on, my warriors. What do you think the slope will represent for this graph? I'm going to pause it at the right moment. Okay. Yep, there we go. There we have it. Yeah, tan theta. All right. So we have the breaking stress right over here. Okay. First of all, let me mark some zones. This is called as the elastic zone. This is called as the plastic zone. This is where it breaks. The slope, believe me, the slope is, what is this? Stress, right? Stress by strain, height by base. What is stress by strain? It is Young's modulus. So the slope will give you Young's modulus. Very good, Chandan. No problem, unforgettable love. It's okay. Yeah, it's always fun. I'm not your very strict teacher who is going to come with a stick and hit you with that stick. Okay? We are all here to have fun and learn. Okay, so the slope gives you stress by strain, which is Young's modulus. Perfecto. Now, some more things. Even before this point, there is another point. Let me call it, I don't know, maybe X point, or I don't know, something else you can call it. There is a point before which, you know, the curve can become curved as well. This graph can become curved. It might show some kind of non-linear behavior. If it shows non-linear behavior in the elastic zone, then this is also called as the proportional limit. And Hooke's law is only applicable in this zone. So in this zone where it is proportional, when stress is proportional to the strain, only there Hooke's law is obeyed. So understand the difference between proportional limit and elastic limit. In proportional limit, stress is proportional to strain. From this point to this point, it is still elastic, but it is not proportional. Understand? Yes, Abhirami, it is exactly for class 11th, be it CBSE, be it ICSE, be it JEE, be it NEET. Yes, you can attend it. So understand the difference between these points. Last thing over here is, if you calculate the area under the graph, let's see what it will be. This is stress height wise, base wise it is strain. What is the area of that graph? The area will be half base into height. Does it ring a bell? Ring a bell. Jagdeep, there is no point brooding over the past. You have one more term to work, you have internals to work on, and you have other papers. Even if the marks decreases in one, it will increase in the other if you work. But if you stay depressed and you cry over the past, then it will not. Okay, so watch my motivational video which I just conducted 1 hour back on this channel, Strategy for Physics. Watch it properly, you will feel motivated. So what do you think it is? This is nothing but energy density. So this is nothing but energy per unit volume. That's what it will give you. Very good. Excelente. Excelente. Very good. Now the last thing over here is, sometimes you will see the graph going up like this. They will show you arrow marks. Arrow marks means, are you increasing the stress or decreasing the stress? If it is this way, you are basically increasing it. If it is this way, you are basically decreasing the stress. From this point to this point, because what is this point B? This is basically your elastic limit. This is your elastic limit, right? The limit till which it stays elastic in nature. So if you remove the stress, it is going to come back here. But by chance, for example, in this plastic zone, if you go till this point, let's say I will choose a point here, and you remove it, so understand it's not a two-way. It will increase till this point, but if you try to decrease, it will not come via the same path. In fact, it will go somewhere here. This is how it behaves. So if you increase till this point and leave it, it will come here. If you increase it till here and leave it, it might come over here. That's how it will look like. What this means, look at this. Here, there is no stress, but there is strain. Look at that bottommost point. There is no stress, but it has deformed. Meaning, it has deformed permanently. It has deformed permanently. When you relieve it, it comes back here, but not to the same shape and size. It has got permanently deformed. So this is also called as permanent set, because it has permanently set itself to a new shape and size. Understood? Yeah. Hope to see you, Jagdeep, tomorrow at 11 o'clock. I'm going to conduct a class. Hello, Simple Girl. Hello, Muthuram. Welcome aboard. So that's what you should know about stress and strain graphs. Let's see some beautiful questions on it. But I have already put up all the theory. A is the basically proportional limit till which Hooke's law is obeyed. B is the point till which material remains elastic. It's also called as yield point. And the maximum point till which it can bear the strength or tensile strength. beyond this it breaks. Okay, so that's what it is. Very good. So what does this depend on? This depends on the material. Okay, whether it is aluminum, whether it is this, that, it depends on that. So some students ask, sir, more Young's modulus, sir, so it has more stress, more breaking strength. That is wrong. See, let me tell you one thing. Just because a material has more Young's modulus does not mean it has higher strength. Imagine it is also possible another graph which has less slope, but it goes like this. Look at this. Look at this. This is material B and this is material A. Amongst these two material, red and black, answer this question. Whose Young's modulus is more? Young's modulus of A or Young's modulus of B? Whose Young's modulus is more? Okay, this is a straight line. I hope you can see that. It's a straight line till here and then it becomes curved. Whose Young's modulus is more? Come on, quickly answer this question. B or A? Obviously more slope. Who has higher slope? A has higher slope. The red graph has higher slope. Look at this, the red graph. The red graph slope is higher. So the red graph, that means A. So it's just based on the concept of slope. Understood this? Yeah, many students make a mistake over here. If I ask you the strength of A versus the strength of B, now whose strength is higher? Yes, Jagdeep, it is. Yeah, from A to B, Hooke's law is not obeyed, right? From A to B, it is obeyed only till proportional limit. Okay, so now the gap between proportional limit and elastic limit is usually very small. Okay, now A strength is less. You can see that this graph ends over here. B strength is more. The strength of B is more. So understand the difference. Be very careful. So the strength of the graph should be seen here. Look at this. B has bigger strength because it breaks later. So where does it break? So these are two different things. How many of you understood this concept? Young's modulus is different from the strength of the material. Strength of the material has got nothing to do with Young's modulus. You can see the inequalities are different. Everybody got it? Please put up a yo, please put up a thumbs up in the chat box. Let's do questions now. Okay, the breaking stress of the wire depends on? Quickly answer this question. It's not inversely proportional, Dakshin. It could be same, it could be more. है ना? I'm saying they are not related. That's all. Sure, Parthan, definitely. Okay, the breaking stress of the wire depends on C. Very good. Material of the wire. Perfect. Proud of you. Looks like you are very attentive during the class. Yeah, it does not depend on radius. It depends on the material. So aluminum has different strength. Steel has different strength. Copper has different strength. Very good. If you have an experiment and the load, basically the stress or basically the force, you can say. This is the force. And there are 4 wires, same material, same length, but different area. Which is the thickest wire? Let's see. Come on. How many of you can solve this question within few seconds? It's not very difficult. I'll give you some hints. Same material means same Young's modulus. Same length, that means original length. Areas are different. And load means force. Extension or elongation means X. Try to think how was the formula. Young's modulus was force by area, extension by length. Let's write it again. So F by A and L goes on the top, X over here. So I think force versus elongation is asked. So F will be YA by L into X. Now basically it's force versus X graph. Force versus X graph. Y is same and the length is same. So you can see over here, this term over here is nothing but the slope of force versus x graph. Who has the highest slope? Who has the highest slope? A has the max slope. If A has the max slope, that means area is also maximum. So the question is, which is the thickest wire? Done? Simple? Got it? Perfecto? Let's move ahead. Next question. To break a wire of 1 meter length, minimum 40 kg weight is required. Then, if you take a wire of the same material but double the radius, then if the length is 6 meters, how much is the breaking weight? Very interesting question. Let's see how many of you can do this. What should be the new breaking weight required? Observe, it's very, very easy, let me tell you that. Come on, think. Options are here, 80, 240, 200, 160. Break a wire, Arun says B. Interesting. Same material means Young's modulus is same. Interesting. Remember, in the stress versus strain graph, okay, it was like this. This is what the breaking strength was here, right? And for a given material, this graph is decided, it is fixed. So when the material is same, not just Young's modulus, but even the stress versus the strain graph is same. If the stress versus the strain graph is same, what does it mean? The breaking stress is also going to be same. What is breaking stress? Breaking stress is force by area. It's got nothing to do with the length. So, to break a wire of 1 meter length, minimum of 40 kg weight is required. If the wire of the same material but double the radius, now this is the part, doubling the radius, if the radius is made 2 times, the area of cross section will become 4 times. Why? Because area is pi r square. So if radius becomes double, area will become 4 times. So if the denominator becomes 4 times, to keep the ratio same, the force should also become 4 times. Understood this concept? This breaking stress, right? It is the same for a given material. So if denominator becomes 4 times, numerator should become 4 times. So 4 times of 40, how much it is? 160. Because this 40 kg weight will now have to be multiplied 4 times. Done. Oh my god, Srishti, I hope you will watch the replays very soon, okay? But all the best, but make sure you watch it. Very good. Now it's time to give you the homework. This is your first homework questions. You're going to put up all the answers in the comment section. This is your second question for homework. Okay, beautiful question on stress strain graph. The third question on homework, here it is. And let me show you all the students who have solved the homework last lecture. So which was my last lecture? Last lecture was simple harmonic motion. And if you have missed it, you should definitely watch angular SHMs and pendulums. It's right over here. Okay, that was the previous class and it was the last class of SHM, but we'll have more sessions on SHM as well. Even elasticity and mechanical properties, we are going to have many sessions on problem solving. Don't worry about it. Very good, Ishpreet. Very good, Roshni. You guys have been consistent. Very good, Dakshin. Very good, Chandan. Very good, Saja. Very good, Haritha. Very good, Gokulnath. And thank you for all the lovely comments. And thank you all the lovely students who are regular and who are attending. And sometimes you might not be able to put up the answers to the homework question, but that's okay. Also remember, my courses are available for you if you are a pro member for free. So free courses of Shreyas sir, Okay, Shreyas sir, for all the VPro students. So if you are a VPro student, then it is absolutely free of cost for 11th standard. So for 11th standard, what are the courses? Number 1, derivations course. All the derivations of 11th standard. It will be helpful for you. Second, HC Verma short answer course. You will see that. Third, numerical problem solving, numerical courses. Also, number 4, Erode problem solving. If you search for this on your phone, on your tab, or on your laptop, enroll more, you will get it. All these courses. Not just mine, but also so many other teachers' courses are just available for you. So you can see lots of micro courses. Kvpy course, there is only 1 month remaining. There is only 1 month remaining for Kvpy. So all the micro courses, crash courses, so that also includes Kvpy SA course. It's again free of cost for all the pro students. That's what you get in pro subscription. And remember, the classes are in English. You get a choice of so many teachers with so much of experience that you don't have to run around different institutes. Not just that, you have tests, you get booklets, assignments, and regular test series, so that you don't have to join 100 test series or subscribe to random tests on the internet. Not just that, you get parent-teacher meetings, parent-teacher sessions, guidance sessions, okay, and then gupshup sessions, strategy sessions, tips sessions, everything, all of this. Now, if you are interested, then I would suggest check out the 3 versions, 3 packages. Yes, Kroto is very good, Zeph, for Olympiads, definitely. You have 3 packages, Lite, Classic and Plus. The Lite gives you live classes, even the recorded versions, access to micro courses, even the notes are accessible. You don't have to sit and make notes, you get the PDF, even if you miss the class. Test series and report cards, notes, assignments, booklets, and doubt solving in the class. That's a 2-teacher model, 1 teacher teaching, 2nd teacher solving doubts. In the Classic, you get on the mobile app, after the class is done, solve all your doubts through the mobile app. And yes, the Plus version gives you a personal mentor. And if you are interested in joining these courses, all you need to do is go in the description box below the video that you're watching. You will see Avail Exciting Vedantu courses JEE 2 years. Click on this link. If you want, you can even change it to some other course. Let's say you just want the Kvpy crash course. You can choose that. You can see the Kvpy crash course is just for 1,800 rupees with access to doubt solving also. Even if you go for doubt solving during the class, it's for 1,800 when you use my coupon code. But let's say you want not just Kvpy, but you want the entire 2-year course. Well, then you just have to go to, where is it? Grade 11th, JEE 21-2023. Everything what I told you is here. And guess what? It's for 54,000 for both the years together. And there is an option for you to buy that complete course. And you can see you save 6,000 rupees. And you can buy this course on 0 interest, no cost EMI option. For 12 months, you get it for 4,500 rupees per month. That is one option. But if you want to try it out for even 15 days, that's okay. 1,350 rupees. Click on it. You save 150 rupees and you get it for 1,350 instead of 1,500. And again, you can pay via Amazon, Paytm, whatever you want to. So that's the beauty of this. I would really be interested to see all of you in the pro subscription, join my courses, join the Kvpy courses, make full benefit of small chapter wise courses, live classes, attend the recorded classes as well. And not just that, the test series, assignments, it's full benefit, full faida. Try it out for at least few days and see how it works. Okay, I've given you all the options available for 15 days, for complete 2 years, all of that. Make sure you use coupon code. If you don't use my coupon code, you cannot get in touch with me if some problem happens. Okay, so make sure you use my coupon code out there. All right, so thank you very much for joining in, and I hope you guys have a great time ahead. Srashti, the right time to solve Erode is now. If you have completed 11th portion basics, then start solving Erode. But if you have not yet completed 11th portion, then don't solve Virodo or Protov. Okay, so thank you. Bye bye. Take care, Aditya. Bye bye, Srishti. Bye bye, Dakshin. Yes, so pedagogy app is also part of Vedantu. It's free for all the pro users. You should definitely make use of it because it gives you access to all the books. So yes, Vedantu has tied up with pedagogy. All the offline books, the soft copy in ebook format is available to all the Vedantu students. That's crazy. Yep. So that's what you get in vPro. Okay, so lots of amazing things coming up. And let me tell you, in the next class of Nurture series, I will start fluid mechanics. Okay, so stay tuned and have a great night and stay focused. Make sure you attend all the classes. And thank you for loving the video. Thank you for hitting the subscribe button. And yes, do follow me on my Instagram. Bye bye. Take care. This was Shreyas here. Hasta la vista.